Okay, let's look at this intro. It illustrates a key aspect of the paper, root cause analysis of Anomaly. Alright, so Figure 1 gives us a nice visual overview of their proposed AERCA framework. It processes both normal and abnormal time series. For normal data, it performs Granger causal discovery, essentially figuring out if one data series can predict another. An encoder derives what they call exogenous variables. These are the independent underlying drivers of the system. A decoder then reconstructs the original series from these. For abnormal data, the framework then uses these derived exogenous variables, looking for significant deviations to pinpoint the root cause of an anomaly. Alright, so this next table, Table 2, shows us the overall performance of that Granger causal discovery part we just talked about. Figuring out those predictive relationships. It compares their AERCA model against several others on different kinds of data, like linear and nonlinear. We see metrics like F1 score, a measure of accuracy, and also AUCPR, or area under the precision recall curve, and AUCROC. These area under the curve scores, well, higher values mean the model is better at correctly identifying causal links. Then there's Hamming distance, where a lower score is better, indicating fewer errors in the discovered causal structure. AERCA achieves perfect scores on the linear dataset, and really stands out on the nonlinear ones too. Building on that strong performance in Granger causal discovery, Figure 2 here really drills down into why AERCA is so effective. This figure shows an ablation study, where researchers remove a component to see its impact. The blue bars represent the full AERCA model, while the orange bars show AERCA without a crucial independence constraint on those exogenous variables. This constraint is enforced using what's called Kullback-Leibler divergence, or KL divergence, a statistical measure of how different one probability distribution is from a reference one. Across various datasets, especially Lotka-Volterra, the full AERCA performs much better, highlighting the importance of this KL divergence constraint for accurate causal discovery. So having seen how crucial that independence constraint is for discovering the underlying causal links, Table 3 now shifts focus to the main event, the actual root cause analysis performance. This table compares AERCA against other methods on various datasets, using metrics like AC at 1, AC at 3, and so on, often summarized as AC at K. This accuracy at K-score, well, it tells us if the true root cause was correctly identified within the top K potential causes suggested by the model. Higher scores are better, and as you can see, AERCA often achieves perfect or near-perfect scores, especially on those synthetic datasets and also the MSDS real-world data, really showing its strength in pinpointing the actual source of anomalies. Okay, so after seeing AERCA's strong performance in identifying the root cause time series, Figure 3 now explores how well it handles anomalies that persist over time. These two plots show the performance of root cause identification as the number of continuous exogenous interventions. Essentially, how long the underlying cause of the anomaly lasts increases from 1 to 9 time steps. Plot A shows average at 10, an average accuracy for identifying the correct root cause series. Plot B shows average star at 500, which measures accuracy in pinpointing the specific time step of that intervention. While performance naturally dips as interventions get longer, AERCA remains quite robust, especially for the linear and nonlinear datasets. Alright, so building on that ability to handle persistent anomalies and even pinpoint their timing, as we saw in the previous figure, Table 4 now provides a more comprehensive look at the overall performance of root cause analysis, specifically at those exact time steps. We see metrics like AC star at K, that's accuracy star at K, where the star really emphasizes that we're judging if the model found the precise moment the intervention happened within its top K guesses. Across various datasets, especially Lotka-Volterra and Lorenz 96, AERCA achieves outstanding, often perfect, scores, reinforcing its capability in this very challenging task. Following those strong scores for pinpointing exact intervention times, Figure 4 offers a really nice visualization of this process. We're looking at a multivariate time series from the nonlinear dataset, with each row showing a different dimension. For each, you see the original data, then the derived exogenous variables, which are those underlying independent factors. Below that, we see the predicted root cause scores, calculated as z-scores. A z-score here, it essentially quantifies how unusual an exogenous variable's activity is. The pink line shows the true anomaly, and the blue line is AERCA's prediction, often lining up impressively, which really helps to see how it works. So that visualization really brings to life how AERCA pinpoints anomalies by tracking those underlying exogenous variables. And that, in essence, is the power of AERCA. It's a novel method that excels at root cause analysis in complex time series, identifying both the problematic series and often the exact timing. The approach cleverly integrates Granger causal discovery by learning these independent exogenous variables, those underlying drivers, using an autoencoder-based framework, a type of neural network architecture which helps it learn the system's normal behavior and then spot deviations. It's a really promising direction for diagnosing complex issues. That's all for this AI Research Roundup. Thanks for tuning in.